This is a retake of the discussion of this slide. We inadvertently lost the rest of the lecture, so we're re-recording it. I believe I finished talking about these graphs, and I've moved on to this graph. If you take all three of these items and you combine them, you get the water levels, the lake levels. And the lake levels, as recorded for the last 100 years or more, in the Lake Michigan Huron area, have quite a bit of ups and downs to them. If we look at all those ups and downs, we see that this is about a meter, both up and down from the average. And so this is each monthly level, so that shows you that there's quite a bit of noise, and some of these are annual and whatnot. The point of this is that there's no time when the balance is exactly in zero. It is always a little bit up or a little bit down. And that averages out. On geologic timescales, those things kind of go away. What we're concerned about is the longer term average. However, I'd like to point out that this meter change actually has, as little as it is, has a significant influence on things like shipping. If the water gets too low, you can't move some of the boats, the grain or the iron ore boats through the Great Locks. Or if the levels are high, you get coastal erosion and the loss of infrastructure like walls, some bridges to some extent, and the most prevalent thing on many of the bluffs around the Great Lakes, houses. So this infrastructure really matters for this meter and a half. That's why the Corps of Engineers tracks it so carefully. And so we had a period of low levels, and we've now got some high levels. You're going to hear a lot more about erosion around the Great Lakes. That finishes up that slide, and now we can move to a summation of all of these. What we just looked at was the yearly average. Now we'd like to think about how is that average distributed through the year. Here's precipitation. It has a certain number per month. This is June to May. The balance year is summertime. It has a certain value, and then it drops off and spikes again. The really kind of interesting one is evaporation. Evaporation we kind of think of as in hot weather. It's always hot, that makes more things evaporate. The reality is a little more complicated. Evaporation is not necessarily controlled purely by temperature. It's also driven by how much water vapor there's in the air. If there's no water vapor in the air, then you get a lot of evaporation. If it's already humid, you can't get much evaporation. And if we take a look at this, it turns out that the most important time for evaporation is in the winter months, not the summer months. So it's not, this is an artifact of this air being dry because it's cold. Cold air doesn't hold as much moisture, it drops out, we've talked about that, and the evaporation is the highest. The third graph on this has to do with the total sum. So in this case, precipitation and evaporation, the area under the curve, so to speak, or every monthly total is here, and we have fairly low levels, and then it spikes up the runoff. So this is the water that's going out of the lake basin. This is the net overflow for the average precipitation. Some of it goes out of the, some of it's diverted. And this is Lake Superior, not necessarily Huron, but the graphs of all of the lakes look similar to this. So there's an interesting annual rhythm or pattern to this. The take-home message is the runoff is controlled by the evaporation and precipitation. Moving on to the next slide. Back to the evaporation. We talked about the humidity, dry in the winter time, having more humidity. There's a second compounding factor, and that's lake ice. And the evaporation of the lake ice has undergone some additional study and some conceptual models that were in vogue 20 years ago are no longer in mode. And specifically, this is September to October, the course of the year, slightly different time than we saw on the other one. And this is a notion of open water, ice cover, and then open water again. And in this conceptual idea, there's a little evaporation in the summertime or the fall. It peaks up a little bit in the winter months, then it goes to zero because of the ice cover. You can't evaporate the water through the ice cover. You could sublimate the water off, but that's a different story. And then subsequently, lower values, and then peaking again in the fall when it gets cold. A newer concept has to do with the extent of the ice, and it turns about that you can get these different things depending on if you have low ice or high ice. In an ice year that has a lot of ice, you figure they shield that for a longer period of time. But that doesn't necessarily cut down the amount of evaporation because this gradient is still high. If it's cold enough to make the ice, then the gradient, that precipitation, moisture in the atmosphere goes low and there's more heat loss. So these conceptual ideas then have been reassessed, and we see that lake ice, moisture in the atmosphere, temperature all have something to do with the amount of evaporation. It's not a simple property and it's very difficult to actually measure. That's why we have the least control on it. Moving along, we set up the problem to contrast two basins. One, the northern Sahara, the top half of Africa, it's more than half, I guess, versus and this is just a portion of the Great Lakes, Lake Michigan and Lake Superior are over here. And so totally these two areas are probably the same. And what we contended was, and I pointed you to the notion that these happened something on the order of 8,000 years ago. And the something on the order of 8,000 years ago means plus or minus 100 years here or there. It also means that all of the things that we're talking about, the annual cycle or the monthly cycle, average out. And so that we can take a harder look at the balance because it's averaged out. We're not worried about one particular year so much. This was a graph to justify that they're the same. Here's all of the evidence from Africa of there being a wet period. And here it's considered the low period is coincident with that. Graphs are roughly the same. With a more complex history, higher levels, but that lower level, and again, that's operating for about 1,000 years. So it didn't happen overnight, it didn't stay there overnight. The cultures had a period of time to adapt to it. Why do we want that? To understand this, the objective of this whole exercise is to give you an appreciation of actually applying numerical numbers to these conceptual properties. And so to do that, we're going to set up a complete answer, or we're going to require that we get a hydrological balance of both today and 8,000 years ago. To keep it simple, we're going to worry about Lake Huron. To keep it even simpler, we're going to make some assumptions to make the math simpler. I think we should emphasize that this is a geology class, and so there's a geologic overprint here. And the geological overprint is having two things that seemingly are different that occur at the same time are probably not coincidence. There's probably some underlying cause to both of them. That could be debated. Most of the studies have a focus on one or the other, the dry area or the wet area, and they invoke some mechanisms to explain that. But the reality is it's probably, it could be much more global in scale, and therefore we might want some time that it's going. So we're going to call it the same practical time. And so what are the implications that you get a yin-yang in the climate system? that was the question, the third question today. You're gonna see it again, the last question that we do in this unit. You might see this conceptual theme later, because I'm basically arguing that these climate systems are more interlinked than we typically give them credit for. So to illustrate this problem, we're gonna go through the caribou migration, 37 meters below the current level of Lake Huron. That implies it has a different hydrological balance. Now, balance is how much the water is there. It's like your bank account. And you've got money coming in and you've got money going out, and sometimes they balance. They probably have to balance over the long run, but they don't necessarily balance at the first of the month. My bank account gets a big surge of money the evening of the first of the month, and then about 2 days later, all that money's gone because I'm paying off some bills. But can we estimate this? And yes, and it's just about like doing your checkbook. So there we go. And let's do a checkbook balance. And a more complicated checkbook would have all of these things. We said this slide before. And you have a lake basin. You have precipitation falling on it. You have evaporation out of it. You have a river coming in. You have a river going out, in and out, stream discharge. And Q is commonly known as water flux. And the Q in and the Q out have to result in the change of, this says, in fancy math, says the change in the volume. Now the volume and area are related, but not the same thing. You see area is in this term over here, and I'm not gonna go through all of that, but we are concerned with all kinds of fluxes. We're gonna simplify all of those down to 2, and that would make a simpler checkbook balance. Here's a more complete word description of all the math we just saw. The water in minus the water out equals a change in volume. Got more money coming in than going out, your bank account goes up. Breaking these two components into precipitation and river flow gives you the same result algebraically. Now, we have to harp on this units per meter, these flux units, this per meter squared, meters cubed per year, because otherwise you can't balance your checkbook. You don't talk about your income in German marks and your outcome in French francs. So you have to normalize this by the unit. The second thing we're going to do is we're going to dispense with those funky math terms on the other one, and we're going to make our lake a box. Therefore, the volume and the, not the surface area isn't going to change, but the volume is going to change in a simple question. So question 1 in the deliverables for this week has to do with balancing it today. How much water's coming in, how much water's raining, how much is evaporating, and how much water is running out. And that number is not going to be 0, as we saw before. Every year it goes up and down a little bit. And so that's the natural variation. Over the long term, it's close to 0. But we'll use the math, and we've decided to supply the numbers in the right units so that everybody has starting on the same point. You don't have to look them up, but you should be aware that we've done this conversion. They may not be exactly your numbers. If you got a 15 on this problem and you want to use those numbers, then have at it. But otherwise than that, the volume is constant, and the water in and the water out have to be the same. If each checkbook is the same, balanced, it's the same going in and going out. What about the next more complicated situation where the volume is not the same? In other words, what about the situation where it changes. Can we estimate how much change would have to have happened, volume change, to get the pathway for the caribou to go between northern Michigan and Ontario along a land bridge that's currently 37 meters below the lake level? So here's our same equation, in, out, change of volume. Now, we're going to assume, and this is the geological thing speaking, that those basins were closed. There were no lakes, there were no rivers coming in, because Huron is fed by Superior, Michigan, and they were both low, so there's no inflow to Huron. By the same token, Huron was low, so there's no outflow. So all of a sudden, we get rid of 2 of our 4 terms. Now, this is a derivation to get down to this formula, but the lake at volume 1 has to be equal to the depth times the surface area. Why am I making the surface area? Because volume is depth times length times width. Time 2, same difference. But I'm relating depth 1 and depth 2 by this minus 37 meters, the 37 we have to go. Now, reiterating that volume is length times width times depth, the volume then is the surface area times the depth. Okay, that's fine. The change in volume then is then 37 meters times the surface area squared. Substituting all that back in, our working equation is precipitation minus evaporation equals 37 times the surface area. Because we keep it in a box, we're going to have the same surface area today and in the past. So you should be able to diagram this with the right arrows in and out now. There's only 2 left. That's pretty simple. They're related this way. It's a conversion factor in your balance. There it is again. What could change to make that happen? What I want to do now is crude sensitivity analysis. We always would think the lake level dropped, that it got drier, that the precipitation changed. But by the algebra, either the precipitation could change, or the evaporation could change, or some combination of the 2 could change and give you the same result. So what I'd like you to do is, after taking out the rivers, I'd like you to examine these 2. So for step 1, after you get the balance of the thing, then keep the precipitation the same, but change the balance to get 0. Change, the evaporation to get 0. Then, the inverse of that, keep the evaporation constant, and lo and behold, change the precipitation to get a 0 balance. So it's a simple algebra problem. That's the essence of question 2. We've gone a little bit deeper into the nitty-gritty now. So, to reiterate this, and we're about winding down, hydrological balance must be 0 if the volume remains the same. In some ways, this is what's called the state of the lake. A hydrological balance compiles all the water inputs and outputs to the lake. This will allow us to figure out what terms are there. But you can't do it if the units are different. And most of your background work on this is not doing the math, it's making sure that the accounting is set up right. You've got all your bills to be paid and all your checks, incoming checks, set up and accounted for. So we got a primary equation for number 1, we've got a rearranged question for number 2, and then you're going to do some balances with it. You're going to manipulate those numbers a little bit. Here's the deliverables For the online group, this is not due at 9, it's due sometime later, it'll be specified. It's the 30 point. Do the present lake balance, get a number. Construct it for 37 years below, get a different number. For the 7 below, to do 3, you're gonna have to do a little experimentation with, was it precipitation or evaporation? There's a range of answers to number 3, so the bonus is more of a thought question. What could cause either the precipitation or the evaporation to change? Changing them, and the amounts of changing them is easy. Why they change is a little more gnarly. Sticking to climate possibilities, why might these give us a lake level different than the bottom? That's the Huron example. We're going to expand on that on Thursday, and we're going to worry about not only the Huron value, but why, in fact, does the planet seem to have a wet area and a dry area playing yo-yo or yin-yang with each other. And that's it for the lecture for today. This would be the end of part 2 that was re-recorded because it was lost in the original commutation.